Welcome back to Risc-V emulation in a high-level language. And I'd like to start by apologizing for my previous update. We really had some technical issues that I was unaware of, and I sent out a whole hour of mute refactoring. Suffice it to say, in the previous session, what I did was pick apart the existing RV-Fun executable into three pieces. There is a new assembler or RV-ASM executable, which allows us to assemble an ASM source file. And then the original Risc-V Fun executable now consists only of the emulator. And they communicate by a file where the Risc-V emulator reads a file that is written by the Risc-V assembler. And in order to read and write and share in mutual common classes, there's a new class library called lib, which contains tools that are used by both RV-Fun and RV-ASM. And towards the end of that session, I was talking about how the raw file format that I was using to save the assembled file was quite limited. It has a bunch of problems. One of which is that the file is hard to identify. It's just a bunch of raw bytes, and an operating system usually wants to know what kind of file it is before it launches it as an executable. A second issue is that there is no way for me to specify at which addresses I want the executable to run. In some architectures, this is really important. You have to be able to say that this executable was linked to assume that it's loaded at position or memory address 1000. And there's no way to specify this in the current method. The binary is always loaded at a specific address in memory. So we want to have the capability to specify that this file should be loaded at a particular address. And then also on modern operating systems, what you'll end up wanting to do is separate executable code and readable and writable data from each other so that they don't overlap, because you don't want the executable code to be writable and you don't want the writable code to be executable. And so what you want to do is segregate the different segments of your program in different address ranges that don't overlap. And this placement of all of the different segments has to be done using some sort of metadata that indicates where in memory what chunk of memory should go and how big that chunk of memory is, and also whether what permissions, what protection that chunk of memory should have. Should it be readable, read writable, read executable, etc. So the file format that we use today is completely inadequate for these kinds of things. So we look around to see if there's any other file format that might be more relevant or more useful. And I quickly look at the executable and linkable format, or ELF format, which should be adequate for the purposes that we're putting our emulator through. So let's take a look at what what is an ELF file or an ELF executable file. It's a standard format for files which consists of a header. As you can see here, there's a chunk at the beginning of the file that describes the contents of the file. And then there is something called a program header table, which contains descriptions of all the segments of that this program defines, or this file defines. And then there's an optional section header table, which defines named sections within the file. Now, the ELF file format is used for multiple purposes. It's used both for executable files and for object files. That is, source files like assembler or the C programming language source files that have been compiled or assembled but have not yet been linked together into a full executable. So in those cases, there are no program headers at all. That part of the file is missing, but there will be section headers describing the different pieces of the assembled output and whether or not they should go into data or a text segment or whatnot. But for the purposes of our discussion today, we're going to focus on a executable file format where you have a program header table pointing to the different segments of the program, but we will not use section headers today. Okay, so what we want to do now is consume this type of files and also create this type of files. And I find it usually quite simpler if you already have a small sample file to play with. I didn't happen to have a small ELF file, so I decided let's just create one from scratch. And so I do what I very often do when I'm writing software. I think, wouldn't it be nice if there were a class that did something useful? And in this case, the something useful is writes an ELF file. So how would I want that ELF file or that ELF building file or class to look like? I would want it to give me the opportunity to define fields in the header. Once I would like to say this is a executable file for Risc-V and it's in little endian format. And then I would like to be able to provide the program headers one at a time. I'd say here's my first section or a segment. I've described it as follows, and then the next one, and the next one, and the next one, until finally when all of the segments have been provided, I can now tell the ELF builder, go ahead and generate the whole file for me, please. So let's take a look at the code. I wrote this code in a previous run, and the sound problems that I had caused the caused that recording to be completely mute, which made it not very, very pedagogic. But now I'm hoping that the sound is going to work. So we'll take a look at this specification document for the ELF file format and look at its counterpart in C#. So the ELF header is the beginning of the file, and it's defined with this C structure here, consisting of 16 bytes in the beginning, which are called the identification section, and then a bunch of other metadata that comes afterwards. So in the C# project, I've created a class called ELF. It's a static class which contains a bunch of constant declarations. So here I've defined the number of bytes in the n indent piece of the identifier. And then also I have defined a few classes. So here is or rather structs, because these we're going to be using these structures to save and load data directly out of the file. So here is the ELF32E header structure, the beginning of the file, and it's pretty much a copy of the structure that we saw here, except translated to C#. For those of you that are unfamiliar with unsafe and fixed, what I've done here is I've used a fixed keyword to tell the C# compiler that this array is an in-place fixed size array, unlike the normal C# arrays, which are always a reference type. So this member here actually occupies those 16 bytes in place. And in order to use the fixed keyword, you have to specify unsafe, because this is dangerous. We have to be very careful that we don't overwrite bytes beyond the 16 bytes that we have in the ident array. And the compiler and the runtime will not stop us if we're using unsafe code. So you got to be careful here. In order to use the unsafe keyword in turn, I had to modify the project file to allow unsafe blocks. So you can see that turned on here. All right, so anyway, so this is a byte by byte, word by word definition of the ELF header file structure. Also notice that I have this attribute struct layout kind sequential here, which tells the .NET runtime that I do not wish these fields to be rearranged in any way. They are to be added and referred to in exactly the order that they are defined in the source code. Otherwise, the jitter and the C# language are allowed to, by the semantics of the language, to blend and move around these fields in whatever order that makes sense from a performance perspective. But here we have a file format that we have to respect, and so now I'm stating that this order of my fields has to be respected. At the same time, we'll take a look at what is known as a program header, which is used to describe a segment. And the program header has a type, which describes what kind of a segment this is. And there are different kinds of segments, but in this example, we're going to be using the segment type load, which means that this segment that is being described is to be loaded at a particular address in memory. The next field, offset, indicates where in the file the bytes that are supposed to go into the segment go. So if you look at the diagram over here, you'll see that this little arrow here corresponds to that offset. It's basically saying the text segment is located in this particular part of the file. Then this field, the virtual address, indicates where we want the loaded data to be placed in memory. This is one of the reasons why we introduced the ELF format in our project here. The physical address we'll be ignoring. It's not really relevant for our discussion. File size tells us how large the chunk of memory is in the file for this segment. So if a segment has 42 bytes, then this number will be 42 bytes. However, there are also some segments that are completely empty. Or rather, they don't need any file data. They are defined completely by their size. For instance, the BSS section in a ELF executable will typically be completely filled with zeros. It makes no sense to store those zeros in a file because it's redundant. So in that case, the file size of that segment would be 0, but the memory size, the space in memory occupied by the segment would not be 0. So we'll be using these fields as well. Finally, the flags indicate whether this segment is readable, writable, and or executable. And we also have to specify an alignment requirement. And the alignment requirement says that this segment, when loaded into memory, must be aligned at a particular a boundary that is aligned to a byte counts of this size. And we'll look into that a little deeper a bit later. The section header we will not discuss in this session. It's there for completeness. So let's take a look at this ELF builder class that I was talking about. Now the ELF builder has a constructor where the caller just specifies whether or not this executable is to be a 64-bit executable or not, whether it's big endian or little endian. It will also allow us to specify the file type, whether this is an executable or a relocatable file or a shared object. And finally, it also allows us to specify the machine type. So the constructor, what it does is it builds up the file header. And according to the ELF spec, we're supposed to initialize the first 4 bytes with the following 4 values, which identify this file as being an ELF file. And so the loader will look for the sequence, and if they're not there, they will refuse to load. Then we check to see whether this is a 64-bit ELF file, in which case we use the constant ELF class 64 to indicate the format of the remainder of the file. Similarly, if we have specified the isBigEndian flag, then we indicate that all the words and half words and long words of this file will all be specified in BigEndian format, which is called ELF data to MSB. If not BigEndian, then we use the LSB for least significant byte first that would be the case for the Risc-V project that we're using. So by default, we'll be passing a false here. Finally, we have to indicate what version of the ELF standard this file is conforming to, and this file conforms to the current version of the ELF standard, which is version 1. Then we fill in the fields that indicate what type of file this is, what kind of machine this is, and redundantly the version again. Then there are some fields which we don't know the values of yet, and we'll have to come back to, but basically we have to specify, or we can specify, the place where the executable is supposed to start executing when it loads into memory. So that's what that's something that we couldn't specify with our raw binary format, but here we have full freedom to specify when executing the emulator, initialize the program counter to this field. Then we have the offset into the file where the program header, the segment definition starts. So this is a pointer into the file where the table of segments starts. So if you go back to this image, it's the ELF header is pointing to this chunk here, the program header table. And the way it does that is by specifying the offset within the table to the header table. And here is the section header table offset, which is initialized to 0 as well. And this corresponds to this arrow over here, which points to the section header table. Actually, there is no arrow that points there, but there is one in the ELF header that points to the section header table. Okay, righty. So then we have the flags. These are the flags for the file. These will tend to be architecture or platform specific. We're just going to use 0 for now because we don't have any special flags here. Then we're going to indicate in the file header the size of the executable header, and we do that by measuring our EHDR structure and putting its size in here. And similarly for the program header entry size and the segment entry size. So the segment headers, the program headers, and the executable headers all have defined sizes that are defined in the executable format itself. We then also have to specify how many program headers or segments we have and how many sections we have. We don't know that yet because this builder is supposed to collect all the segments from the caller, and the caller did not specify those yet. Then we initialize a few lists, a list of segment headers. This is the list that we'll be maintaining as the user adds new segments to our binary. We have the corresponding data for each segment, and then also the addresses at which these segments are getting loaded. Actually, I should probably call this offsets now that I think of it, so let's do that. Okay. So we have a property called entry point address, which allows us to get and set the entry point of the program. And then this very important method is the add segment method, which allows the linker to specify that it wants to create a program header for the segment with a particular segment type at this virtual address. Here is the data for that segment, and that data can be empty for the case when we have a section that has no initial data. The memory size of that section, or segment, sorry, and then the access mode for this segment, and finally the alignment of the segment. And so what we're doing here is just hanging on to all these pieces of data. We first take the access mode, which is our own structure or enum, and we translate it into the corresponding bit flags for the ELF binary. And then we create a segment header where we initialize the type and the address. The physical address is not interesting for our example, so we'll ignore those. Then we take the file size, which is the data that we want to store in the executable file that we're making. But sometimes data is empty because we have, for instance, a chunk of zeros that we wish to store. So we have to also specify a memory size. But if we do have the data, it's redundant to also pass the memory size. So we allow the caller to specify the memory size as 0, in which case we then use the size of the data length, or the length of the data bytes for the memory size as well as the file size. Otherwise, we will use the memory size that is specified by the caller. We set up the flags and the alignment, and then we add this newly created segment header into the list of segment headers, and then the segment data is added to the list of segment data. So this is the add segment call then, and then if we look at a sample code that uses this, I added it to our RV-Fun executable. It's going to be here in test, and what it will do is it will create an elf builder, and we're passing in the flag false for the is 64-bit because we are running everything in 32-bit. We are making the endianness not be big endian. That is, this is a little endian binary because not only the host platform that I'm working on, which is an x86 machine, but the target platform, which is a Risc-V system, both of them are in little endian mode. Then I'm specifying that this is an executable file that I want to build, and I'm also specifying the machine type. This is a Risc-V executable that I'm building. And then I add my segments. I'm saying here I want to add a segment that I want you to load. This is not a metadata segment. This is an actual loadable segment. I want you to load it at this address. And here is some initial data that these are the ASCII characters HI. So we will be able to look at that in our debug dumps. This is the optional memory size that I mentioned earlier because we already are sending the data in here as a non-zero array. We don't need to send the size a second time, so we'll just send 0. And then we tell it that this data is to be read-only, and we want it to be aligned in a 16-byte boundary. Just for fun, I'm going to change this so that it gets aligned on an 8-byte boundary. Let's see how that works. So the second segment will be loaded at a different address. It will have different contents in the file, and then it will have a different access mode of read-write. Then we open a file on disk called a.out to write to it, and then we write to that file. And this concludes the generation of a file. So I got as far as write to stream when I realized that there was no sound in my previous recording. So this one, we finally start live coding again. So let's go and take a look at what we're trying to do here. So by this point, we have collected all of the segments and all of the information that we want from the user, but we have to lay out all of the segment data and all of the headers in the file itself. That is, we need to compute the offsets, the file offsets of all of these pieces before we can write them. So let's go to write to stream. And the first thing that we can do is we can write the header. That's easily done. We will just let's see. Now we have to use. Let's see, was it called Marshall? Span marshaller. That's one. Memory marshaller. And what we want to do then is create a span on top of the header. And the span is of length 1. So we now have a header span. And then what we're going to do is do the equivalent of a cast in the C programming language. We're going to interpret that span as a sequence of bytes. So we want to cast the L32 header to a sequence of bytes. And we have to pass in the span, of course. There we go. So what we have now achieved is we've taken a reference to the file header, which was the structure L32EH header, which we have right here, and we have converted it into a byte span. And now what we want to do is write that to our file. So we'll say file.write and then the byte span. So but now we've written the header. But now we need to compute the positions of all of our headers, and then the positions of all of our files. So we will compute the segment file offsets and store them in the segment offsets array. And then we're going to write the program headers and then write the segment data like this. So let's implement these generate the methods, and then we'll implement compute segment file offsets. So consulting the image again, what we've done is we've written out this big blob of bytes, and now we need to compute the locations of each one of these segments. So what we'd like to do is skip the program header table, or the space that is occupied by the program header table, and then position ourselves nicely aligned so that we can start writing to text. So what we're going to do is we're going to say u int file offset, which is the current file offset, and the current file offset is going to be the size of the executable header, which is file header dot executable size, and then we need to compute the number of components or segments. So the segment headers dot count multiplied by the size of a segment header or program header. And this should give us a position that has skipped both the elf header and all the program headers, because we can't, we need to make room for the program header table. So this is what this has done. And then what we're going to do is we're going to loop through we're going to create a list of positions of the resulting file offsets for all of our segments. And then we're going to, for each one of these segments, we will want to align the file offset to the appropriate alignment that is required by the data. So we will say file offset is equal to align up, file offset, and then the segment's alignment. So what does align up do? What it will do is, first of all, let's make sure that we're not passing a 0 here, because that will throw an exception. So what we do is we take the value and we add the alignment +1 or -1, and then we divide all of that by the alignment, and then we multiply it back up by the alignment. So what this will end up doing is round up, in a sense, the value to the nearest chunk of this size. And then we return that as the result of our call. So, for instance, if we had the value 15 and we wanted to align to a 16-byte chunk size, then we would take the 15, add 16 to make 31, subtract 1 to make 30, integer divide that by 16. 30 divided by 16 is going to be 1 with a remainder of 14, but the remainder we discard, so we get a 1, and then we multiply that by the 16 again, giving us a 16, which correctly rounded us up from 15 to 16. So now we have a file offset. And now we can put that in our list of file offsets. So we'll say file offsets.add file offset. And then what we'll do is we will compute the next file offset. That's going to be equal to the current file offset plus the size of this segment, which was stored in mem size. No, file size. Yep. There we go. All right. So then with the next segment, we will get its alignment. We'll take the file offset and force it to be aligned and allocate the next file offset. And this will repeat until we've done all of our headers. That looks good. And then we return our list of file offsets. Good. So now that we've computed the position in the file where all of these structures go, we're now going to compute, we're now going to write the program headers. So we need we have a loop for this. So let's go to the function, and we're going to iterate through all of these program headers, and we're going to assert that the segment headers count is equal to the segment data count. And we also want to assert that the segment headers count is equal to the segment offsets count. This is just a sanity check to make sure that our program is correct, because we're going to be indexing into these lists using integers. So we'll use for int I equals 0, I is less than segment headers dot count, standard for loop. And so what we want to do now is get a header from our list, update its file offset to be the corresponding segment offsets, and then we want to do the same thing we did before, which is to create a header span, and that is going to be equal to memory Marshall create span on the segment header. And then we want to create a byte span, which is memory Marshall cast from the type ELF 32P header to byte, passing in the header span. And now we can write, but we need a destination to write to, so we need a stream. And in the stream we will say looking good. However, we also have to take into actually no, this is correct. This writes the segments right after the header. So this is correct. So this will loop through every single segment header, updating its offset field accordingly. We also, I just remembered, there's a field here in the beginning of our structure, the program header offset field. We actually know where this goes. The program header offset is going to be right after the elf header, which has a known size. So we can just make the offset equal to that known size. Let's do that. Let's make that program header offset be equal to the elf file header size, elf header size. So this will initialize it to the correct value, pointing it to the right place. Okay, good. Then here, write program headers needs to pass in a file. Let's make this not a file stream, but just a abstract stream. Okay, so at this point now we've written all the program headers. Now it's time to write the segment data. And we have a requirement that these segment data be aligned. So we need to respect that by writing the data at those offsets that we computed earlier. So let me illustrate. So we'll use the same tactic again. We'll do the assertions again just to clarify intent here. All right, so we're going to be looping through each one of our segment headers again. But this time we're going to read a file offset. And that's going to be from, actually, yeah, let's do it from offsets like this. So file offset equals segment offsets I, like this. So now we have the file offset that we want to write to, but it could be that our stream is not positioned at that particular file offset yet. So we have to, if the file offset where we want to write the data to is further along in the stream than the stream's end position is right now, we have to fill the remaining space with some padding bytes. So we need to compute, or we need to determine when that is the case. So we need to first do an assertion, of course, to make sure that the file offset that we're trying to put this item on is not out of bounds. So we'll assert that the stream's position is less than or equal to the file offset that we want to write to. If that's not the case, if the stream position is bigger than the file offset, then whatever was written previously took up too much space. We basically are out of order in our computation of positions. So this should never happen. However, we do wish to write a number of bytes. So if the position is less than the file offset, so we'll need to compute the number of bytes to write. So n padding bytes is going to be equal to the file offset minus the stream position. And, oh, that's also okay. And so while the number of padding bytes is larger than 0, we write a padding byte. So we'll say stream.write byte, passing in a 0, and then decrementing the number of padding bytes. This will write the padding before the file offset. And then what we do is we take segment data of I, the actual data that we wish to write, and write this to the stream. Okay, so there you have it. That writes the data of the object. And so finally, we should have the code that writes an ELF file. So now we will want to verify this. So let's go back to our program and we'll rename this to generate file. And then we will create another method called dump file. Simple enough. And so what we'll do in dump file is we'll take the file that we wrote here called a.out and we will suck it all into memory. So bytes equals file read all bytes a.out. Now we have a chunk of bytes. We're going to create a memory object. And then we're going to allocate a chunk of memory inside of that memory object. We'll give it the address 0, and we'll give it the bytes we'd read in, and the access mode is irrelevant here because all we're doing is dumping them, but we have to specify read. Okay, so now that we've done this, we can now create a dumper. Now that's not the dumper I want, it's a hex dumper that I want. And we pass in the memory that we created, and then we say dumper dump, starting at the address mem, actually address 0, and the length is going to be bytes.length. And we're going to write that to the standard output. So console.out. So what this does, it will dump the file that we created in this part here. So without any unit tests, just raw dog in it. Let's see if this even works. And then we'll have to debug it. So let's run. Oh my goodness, the output's a little confused because we have another dump going on there earlier. But this looks very good. We see the 7FELF signature in the beginning, some of the flags that we set in the identification section, and then some other bytes. But the true proof that this actually is a valid ELF file, we can determine that truth by using an official standard tool to measure the size of the file, so or to inspect the contents of the file. So there is a program called objdump, which I will use to look at a.out, which is right there. Okay, so this is tells us a little bit. It tells us that this file is an unknown architecture, but it's an ELF32-bit little endian format. What happens if we try to load the program headers? It fails. So it can't find the program headers. So there's a bug somewhere that we need to fix. But I want to try an experiment. I want to change the target architecture from Risc-V to ELF32, and let's see if, or I386, and let's see if that makes a difference. Let's build this and run it. Yeah, so it did indicate that it changed the format to I386, but there's something wrong with our headers. Okay, so in order to debug this, we'll need to be able to read our file back into memory. So let's create another file called elf-loader, and then let's use that to debug the problem that we're seeing right now. So elf loader is a new file. Let's create it here. And let's give it a namespace first of all. Oops. So the elf loader will have a load. We'll give it a stream to read from, and we will have in this a public member, an elf32 executable header, and then we will have an array or a list of the program headers. In our constructor, we will initialize the segment array, and then in our load, what we'll do is we'll do the same memory marshal trick, where we create a span of type EL32 elf header, and it will have a reference to this.header of size 1, and then that will give us the header span, and then we need a byte span equals memory marshal cast, so we cast 2 bytes. Nice, and so now we can read from the stream into our span. So we'll say stream.read byte span, and then that will return the number of bytes read. And ideally, we should be checking for errors here. The next thing we should do is then verify that this actually is an elf file. So if header ident0 is equal to 7f, let's make a method called if not is valid magic number, then throw new bad image exception. We'll throw an exception like that, and so here we'll add a new method, and it will say if header ident of 0 is equal to 7f, and this needs to be put in an unsafe context because we're accessing members of an unchecked array here, which is dangerous. Let's do that. If that is true, and the next character is a capital E, and the next one is an F, then we just return this. Good, so now we've checked that this is a valid elf file. If the assumption proves right, then we can read the remainder of the file. So at this point, we've read the header, and I'd like to put a breakpoint right here and then see what happens when we use this loader, because there seems to be something wrong with the file that we wrote. So we will put a breakpoint here, and we will create an elf loader, elf loader, and then we elf loader.load. We pass in the stream. Let's do this over here. We open the file for reading. We then pass it into our elf loader. And then we can investigate what's going on inside the... oh, I think I know what the problem is. We never wrote the number of segments that we have. That's what I think is the problem. So if I go back to the elf builder, we have written a bunch of segments, but we have to update the header. So we need to update the header before we write it, and we have to say this.file header.epnum. The number of segments needs to be the number of segments. There we go. And that's a short. Okay. All right, that's that very likely is the problem. But we have, we can keep this code anyway. We might be using it for later debugging. Okay, so let's try running now on generating a file. Okay, and then we go to our elf. That's more like it. That's more like it. So here we can see how we've specified the offset within the file at address 80. That's where our first segment is loaded. And if we look at 80, we'll see the two letters HI, which is correct. And then we're indicating that this needs to be loaded at address 400. And physical address we ignore. It's aligned to a 16-byte boundary. We also say that on disk, this guy is 2 files big, and in memory, it needs to be 2 bytes big as well. And then the flags are read and read write. Okay, so this looks very good. Let's switch it back to Risc-V in the program, because that's more honest to what we'll be doing soon. All right, let's do this. And then we run it again. And that looks good. All right, nice. So we now have we're pretty convinced that this is a working writer. Now we are ready to start loading this executable into memory. So let's take a look at our main program, the assembler main program, which is over here. And it says right now the linker is creating a single blob and then just writing it straight out to disk. So we want to replace this code here with logic that knows how to write multiple sections out to an ELF file. Now, currently, our linker and our assembler only can handle a single section, which is fine. So what we'll do is we will do the following. We will, after doing all the relocation, we will create an ELF builder. Again, this is not 64-bit, it's 32-bit. It's not big endian, it's little endian. It is a file type Risc-V. No, sorry, it's an executable. And machine type is Risc-V. And then we write the single segment, which is coming out of the section that we just relocated, which is now in memory. Aha, okay, so this gets tricky because this section here will be the memory before we relocated it. Okay, so we'll use this wasteful, and we'll have to use the same mechanism here, bytes to write. So we get the assembled chunk of bytes, compute its length, then we extract the span that we wrote into memory, and then we will add it to our ELF file. So the segment is a load, pt load, because we want to load it into memory. The virtual address is going to be now this base address that we've been using everywhere. But now this is not going to be hardwired. This is going to be optional. We can change this in the future. Then we have the data itself. And then the access mode is going to be read and executable. And then the alignment is going to be the page size. So we'll make it memory bytes per page. Okay, that added a segment. We're missing something. Oh yeah, we're missing the 0 for the memory size. Okay. That's our single segment, and then after that, we will say ELF builder. Yeah, ELF builder write to stream a.out. No, we need to create the stream. All right. So we'll create all right, good. And let's give that a whirl. So we'll build everything. And then go over here. Set up our paths. And then we will try rvasm. rvfun echo.asm. And if we're lucky, there's our code. And of course, the real truth is if we can get Rieko to disassemble this file. Let's try that. Looks like it liked the file format anyway. So what did it discover? So something is not right here because Rieko wasn't able to make any progress. We didn't specify an entry address. That's right. So Rieko doesn't know where to start. So what we need to do here is elf builder dot entry point address equals base address. And remember, this is now completely flexible. We can change the entry point address at any time. But for now, we're going to use the base address as before, and then we will run that command again, and then dump the file again. And now hopefully nope, still not happy. Let's see what happens when we write to stream. We want to verify that that entry point address is, oh, it's the wrong one. No, wait a minute, it's not. It should be that address. So let's, before we write out, all right, let's build this and let's see if the assembler is behaving correctly. And it looks good. Start address is correct. Not sure why Rico is not liking this. There we go. All right, so yeah, so Rico was able to load the ELF file that we created with our assembler, and this looks very nice. This is exactly what we wanted it to do. Good, so we are now able to create files. How about we now load the executable from the ELF file? So let's go back to RVFun, the main emulator program here. And what we'll do is we will modify the, first of all, we no longer need these two test programs, so we can remove those two procedures. We've satisfied ourselves that this is working, and what we'll do is we'll remove this redundant scope, and we will reformat the file. And now we no longer need to have the base address. The base address will now be coming out of the ELF file. So what are we going to do? Instead of doing this, what we're going to do is we're going to do var elf loader equals new elf loader. And what we're going to do next is make this a function. Like this. We'll make that a method. We'll put it at the end here. We will use the file name. So we have an elf loader. We now We need to create an elf stream, so we create elf. Let's see, using var file equals file dot open read file name, and then we say elf loader dot load, passing in the file stream. That should load, but we haven't implemented the loading of the file segments yet, so we'll need to do that. Yeah, let's do that. So that loads the file. Then we should be able to extract information out of the loaded executable, but we're not there yet. So let's go back now to the elf loader, and here we have loaded the header, but now we need to load all of the segment headers. So load passing that in, and what that does, it needs to loop through each one of the number of program headers that we have here. And what we do then is we do something very similar. We have a header span, which is going to be a memory marshal of create span. We need a header here, which is going to be a new program header. So an empty program header, we're going to create a span on that header. And it needs an external argument. Interesting. Now, why is that? Let me make sure that that is the... Oh, that's a Rico structure. We don't want to use that. Let's get rid of that. Yeah, that's more like it. Okay, so now we have the segment header as a span. Now we need to cast it to a byte span. And now we need to take the stream and position it at the appropriate file offset. So we'll need to put it at the, actually no, we already, we need to do it first here. So we say stream.position equals e.header e underscore program header offset. There. So now we've parked the input position of the stream reader to that position, and then we'll just read them in consecutively. They're all one after each other. So we'll say stream.read into the byte span, and that will now become a header that we can then add to our segments add header, like that. That loads all the segment headers. Good. And then that we're done with that. But now we also want to load the segment data. So that will look similar to this. another for loop. And here what we'll do is we will allocate a chunk of memory that is of the right size. So data equals new byte, and the size is the memory size this time, F32. I'm sorry, it's going to be the header that we read. So memory size. So what we've done here is we've taken one of the segment headers. Let's rename this to segment headers. And inside the segment header, it has an indication of how large the memory should be that the segment should occupy. So we allocate a chunk of memory with that size. And then what we're going to do is we're going to position ourselves at the position where that data is located. That's going to be on header.offset. And then we're going to read, and first we're going to assert also that the header.file size is less than or equal to header.memory size, because we don't want to read from the file more bytes than there is in the memory. So then we'll do stream.read, and we're passing in a buffer, which is going to be the data there at position 0 and the file size. So now we've extracted that chunk of bytes and loaded it into data. Now we're going to add it to another list where we have segment data, add data. And we need to create that array. Like that. And we need to initialize it like that. And there we have it. Now that should load our executable, and we will now have nice segments. So now what we can do is go back to our emulator, or sorry, our the main program of our emulator. And here we will now create a memory, and then we're going to loop for int I equals 0, I is less than lfloater dot segment headers dot count. We will allocate a segment for each one of the segments, where we, instead of using a hardwired base address, now we will use the one from the elf file. So var header equals elfloader segment headers of I, and then we take its memory address, which is going to be hdr.vadr, and the bytes are going to come from the segment data member variable. So data equals segment data. There we go. And then the protection, need to compute that. So we'll say access mode equals 0, mode equals 0 if header.flags and elf.pf, if that is not equal to 0, then we are requesting read access. So that becomes read, write, execute. Good. So now we've allocated a segment, and so things should be pretty ready to go here. Then after loading, we need to return the memory that we created here. After we load this, we also need to, we also need a starting, we need to initialize the starting of the program. Where do we do that? I think we do it here. Yeah, the start address. So we need, all right, well, let's do this. We'll break this out and pass in an elf loader. Like that. And then here, the file name is a.out. How about that? And now the base address will be coming out of the elf loader dot header dot entry. Could it be that simple? Let's give it a try. All right, let's get rid of this breakpoint. Oh my goodness, it ran on the first try. How rare is that? So here you can see how the output that we were expecting came out of our program. So what an achievement. We are actually now loading a Risc-V elf binary. So let's verify this. Let's make sure I'm not lying to you. So I can say RV fun. And then a.out, and then this is a test. And look at that, it works. Fantastic. So we are now able to create elf files, and we're able to read them back in, which is amazing. So the next step now is to change our assembler so that we can generate not only the single segment that we are using today, but also more than one. We should be able to add as many segments as we would like. So this concludes this today's session. I hope you've enjoyed it as much as I do. Again, I apologize for the audio problems, and hope to catch you again soon. Take care.